Welcome to this video on linear regression. In this video we will be talking about how do we use and how do we interpret the coefficients of dummy variables. We start this video by talking about the differences between continuous and categorical variables. Our linear regressions always have a dependent variable and a series of regressors or independent variables. And so far we have always worked with a continuous dependent variable. In this particular video, we will be talking about the salaries of professors in the United States. So salary could be our dependent variable, which is continuous. Other potential continuous variables that we could use as regressors to explain variance in salaries are, for example, tenure, how many years a professor has been in an institution. Another continuous variable could be the number of courses taught by this professor, or also in research institutions, the number of publications this professor has may have an impact on his or her salary. However, there are also categorical variables, which are not numbers. And for instance, we could test if gender is associated with salary, which we actually hope is not associated with salary and that there are no differences in the salaries or incomes of women and men in the faculty. We can also talk about a professor's qualification and rank, but I'll leave the description of these for later. Another category could be a professor's department, and a professor could earn differently if he or she is in the finance, in the strategy, marketing, or IT departments. The universities can distinguish themselves by how much they pay to their professors, and also the city, the cost of living of a city, could influence the salary of a professor. However, note that all these are categories, not numbers. And there's a problem in how do we choose to represent these categories by using numbers. We need numbers because the linear regression models assume that the variables, the x's, are numbers. This is how the model works. Continuous variables are already numbers, but what numbers should we use to represent the categorical variables? Should we assign 1, 2, 3, 4 for 4 different cities? Or maybe 100, 200, 300, and 400 for the 4 different cities? It's very hard to tell. Moreover, if we assign numbers, we might be assuming an ordering of the categories in the sense that, for example, being in city A is more than being in city B and more than in city C, which makes little sense. And implicitly, by using these kind of numberings in our models, we're given the coefficients of these categorical variables a slope that usually makes little or no sense whatsoever. So how do we solve the representation of categorical variables in linear regression models? We do this by using dummy variables. A dummy variable is a binary variable, which means it takes a value of 0 or 1 and no other values that will represent if an observation belongs to a certain category or has a particular attribute. They're also called indicator variables because they will indicate if a particular observation, in this case a professor for example, has a particular attribute or not. And in binary notation, also in computer science, usually a 1 represents a yes and a 0 will represent a no. So following this tradition, we will use a 1 to represent if a certain observation belongs to a certain category. The name is funny. We call them dummies because they're not real. They're just there to represent something else. And once we convert the categorical variables into binary variables, what we're going to have is a series of zeros and ones. Once again, the data we'll be using for this example is professor salaries from the US. And we have data from over 26,000 professors in the US, and we know several attributes of them. We know their salary in thousands of US dollars per year. This is a continuous variable and is going to be our dependent variable in our models. We will be investigating what professor attributes determine that professor's salary. And we're going to have 2 different attributes of them. One is going to be their qualification, which is going to be a categorical variable. A professor can either be an academic or a professional. An academic is the usual professor who does some research and works in a university, but a professor could also be a professional that works in industry and simply takes the teaching position as a part-time job. This is a CEO of a firm, for example, that has taken a sabbatical and comes to teach at a certain university. We also have their rank, and here we have several categories. A professor can simply be an instructor, or he can be a tenure track professor who starts off as an assistant professor, then ascends to an associate professor, and finally becomes a full professor, or just professor. And in general, we would expect that the income of these professors will increase as their rank increases as well. So just to better exemplify what we're looking at, this is a sample of our data where we see that there are two categorical variables, qualification and rank. And they're going to have one of the values we just described, and we have a continuous variable which is going to be the salary. To further probe how this data looks and how the things behave before running any models, we're going to look at some graphs generated in Tableau. This first graph shows a histogram of the salary for the entire population of over 26,000 professors. Note that even though it has a right tail driven by some outliers, overall it is centered between $50,000 and $100,000 per year. In fact, the mean value is $112,000 for a given year. Now, on the left-hand side, I'm showing you the distribution of qualification. And you can see that there are many more academics in the dataset than professionals. About 86% of the observations of professors are academics. Meanwhile, only close to 14% are professionals. And on the right-hand side, we show box plots for the salaries of these two qualifications. You can see that most of the outliers in the higher end of salaries are academics, and across the different percentiles, in particular the median, academics tend to earn more from professionals. So we could expect, once we run our models, that we find that academics indeed earn more than professionals, and we want to quantify how much. If we look at the distribution of ranks across the population, we see that only a minority of the population of the faculty are instructors. There are many more assistants and associates, and the majority, 33% of them, are professors. Correspondingly, as one would expect, the box plots indicate that there's a tendency in increasing of the salaries as the ranks go higher, in the sense that instructors earn the least, assistant and associate professors earn similar wages, it appears, and the professors, the full tenured professors, are the ones who appear to be earning the most. At least that is what we get from graphically comparing their medians. If we combine both categorical variables and see how the salaries differ by rank and qualification, we observe the following. In this case, the different columns represent the ranks, and we use colors to represent the different qualifications, whereby academics are shown in orange and professionals are shown in blue. We also use the size of the circle to represent how many of our observations belong to each of these individual subcategories. So they don't tell us anything about the salary, just something about the mix of the population. Since our vertical axis is the average salary, we can see that for every single of the ranks, academics on average always earn more than professionals. We see that the orange circles are always above the blue circles. Moreover, as we go across the ranks, we note that there's still an upward tendency where, regardless if the professor is an academic or a professional, as the rank goes higher, so does the average salary. And keep this graph in mind because we're going to be coming back to it when we conclude this video. Alright, now that we know how the data looks like and more or less who should earn a higher salary than who other, let's start running some models to test this. We will first start testing the difference in salaries between academics and professionals. And for this, we're going to analyze the qualification category, which has two potential values. And what we're going to do is that we're going to create a dummy variable to indicate if a faculty belongs to one of these two categories. In particular, we're going to create a professional indicator. There's going to be a binary variable that's going to have a value equal to 1 if that particular observation, if that professor is a professional, and it's going to be a 0 indicating that it is not a professional, which in this case means that professor is an academic. Note that we only need one variable, one binary variable to represent two categories, because the professor is only going to be on one of these two categories. It's either going to be a 1 or a 0. Once we convert our categorical variable into a dummy variable, in this case we took qualification, and based on the values we constructed the dummy variable professional, we see that whenever qualification is an academic, we have a no or a 0 for professional, And conversely, when qualification is professional, we have a 1 for professional. Now we're going to regress salary on qualification. And this is going to be our baseline model. We have an intercept and we have a slope for professional. Now let's make a small pause here. What does beta 1 exactly represent, and how do we interpret it? I'm going to give you a few moments to think about this. Traditionally, beta 1 would represent a slope, which represents how much will the dependent variable change for every unit change in professional. In this case, the unit goes from 0 to 1. So beta 1 will represent the change in salary when professional turns from a 0 to a 1, which is exactly what we want to test. What is the change in salary when someone goes from being a professional to being an academic, or vice versa? And let's do some simple algebra here. What is the predicted salary for an academic under this model? Note that if a professor is an academic, then the professional variable is going to be a 0. Thus, the expected salary when professional is 0 is going to be beta 0, the intercept, plus beta 1 times 0, which means we cancel out the beta 1 and we're only left with our estimate for beta 0, the intercept. So in this case, the intercept is going to represent the expected salary for an academic when professional is 0. Conversely, what happens if the professor is a professional? In this case, professional has a value of 1, case in which the expected salary is going to be beta 0 plus beta 1 times 1, or the sum of the two estimated coefficients. Almost always when we are using dummy variables, what we're trying to do is test how a dependent variable changes depending on the different category attributes. So in this particular case, we already know that the salary of an academic and a salary of a professional are given by those estimates, and what we would be interested in testing is what is the difference between the two? Does one category earn a higher salary than the other? And note that if we subtract one from the other, beta 1 is really representing that difference. Beta 1 is the added or subtracted salary that a professional earns relative to an academic. So we can do formal tests based on the value of beta 1, the estimated value of beta 1. If beta 1 is greater than 0, then we would be finding that a professional faculty earns more than an academic faculty. If beta 0 is close to 0 or is insignificant, it means that it doesn't matter if a faculty is a professional or an academic, the salary is going to be the same, which in this case would be represented by beta 0. Finally, if beta 1 happened to be negative, that means that a professional is earning less than an academic, which is what we expect. This is the regression output from our model. Note that we have an intercept of 119, and the coefficient for our professional dummy variable is minus 49. Also, note something that is very important for our forthcoming analysis. The coefficient for professional is statistically significant, which means that it is statistically different from 0. If we computed the confidence interval based on the standard error of 0.72, we know that there's no way that that minus 49 would turn into a 0. Moreover, the p-value is pretty much a 0, which means we're very certain that 0 is not within the potential values of the professional coefficient. So recapping that this was our model, we found the following two estimates. And let's start interpreting this. What was the expected salary of an academic? Remember, if a professor is an academic, that means that the professional dummy is turned off, it is a 0, and we are only left with beta 0, implying that the expected salary of an academic is 119. We can also easily compute the expected salary for a professional, case in which the professional dummy is turned on, so we add up the estimates of beta 0 and beta 1, and we find that the expected salary of a professional professor is 69.70. And we were also interested in testing if the two categories earn different salaries, which was given by beta 1. And we find that beta 1 is negative and statistically significant, statistically different from 0. So we can conclude from this analysis that academics earn more than professionals, as we had expected. Our understanding of how we can use a dummy variable to distinguish between two categories makes it a lot easier to test differences across more than two categories. And in this case, we're going to start working with the rank categorical variable. Recall that rank had four potential categories: instructor, assistant professor, associate professor, or full professor. However, if we used a single dummy variable, we can only distinguish between two of them. It's only a 1 or a 0. What we will do to solve this issue is we're going to use more than a single dummy variable. And in this case, we will be using 3 dummy variables to represent the 4 different categories of rank. Note that we're leaving one out, and you'll find out why soon. For now, it is important that you learn this rule. Whenever we want to represent k categories, we will be using k-1 dummies. We always leave one category out. So how should our model look like? Let's start by constructing the dummies, and remember we need to leave one of the categories out. It is very standard that we leave the least important or the lowest value category out. So in this case, we're going to be leaving out the instructor category and construct dummy variables for the other 3 categories. Namely, we're going to create a dummy variable called assistant, which is going to be equal to 1 if the rank is an assistant and is going to be 0 otherwise. We're going to have another dummy variable for associate, which is going to be equal to 1 if the rank is associate and it's going to be 0 otherwise. And finally, we create the dummy variable for the full professor, which works in the same fashion. If we put all these together, we find this model right here. Note that we have an intercept and one coefficient for each of the 3 dummy variables we just created. And a very important attribute of these dummy variables is going to make their interpretation easier. Note that whenever any of these dummy variables is a 1, all the others are going to be a 0. So how can we use this to know what the expected salary of each rank is? Let's start thinking about the instructor professor. An instructor is not an assistant, not an associate, nor a full professor. So all 3 dummy variables in the model are going to be zeros. Thus, we are only left with beta 0, the intercept. So the expected salary of an instructor is going to be whatever estimated coefficient we find for the constant term, beta 0. If we now have an assistant professor, then only the assistant dummy variable will be turned on. The associate and full dummy variables are going to be turned off, which means we're only left with beta 0 and beta 1, and correspondingly the sum of these 2 coefficients is going to be the expected salary for an assistant professor. Following the same logic, the expected salary for an associate professor is going to be beta 0 plus beta 2, and finally the expected salary for a full professor, beta 0 plus beta 3, because once again only the full professor dummy variable is turned on in this case. And to very quickly clarify this, let's see how the dummy variables look in the data table. And we see that whenever the rank is an assistant professor, only the assistant dummy variable is turned on. When the rank is an associate professor, only the associate dummy variable is turned on. When it is an instructor, none of the 3 dummy variables are turned on. And when it is a full professor or professor, only the full dummy variable is turned on. This is the regression output. And if we write down our model, we end up with an intercept of 65.25 plus 41 times assistant plus 45 times associate plus 72 times full. And note something that will be very important as it was before, that each of the different coefficients for each of the dummy variables is statistically significant. So whatever differences in salaries they represent, we are certain that they are statistically significant. So once again, if this is our estimated model and we would like to know, for example, what is the expected salary of an instructor, that would imply that all the other 3 dummy variables for the ranks are zeros and we are only left with the intercept, so the expected salary of an instructor is 65.25. Now, what would beta 1 or 41.71 represent, which is the coefficient for the assistant? This 41 represents the difference in salaries between the instructor and the assistant. And remember that the coefficient for assistant, that 41.71, was statistically significant and different from 0. So we know that the difference is there. Very similar, the difference between an associate and instructor is going to be represented by the coefficient for the associate dummy variable, and the difference between the full professor and the instructor is the coefficient for the full dummy variable. Overall, note that we follow the expected trend, and you can start seeing that the higher the rank, the higher the wage. But let me ask you a tricky question. What is the difference between an assistant professor and an associate professor? I hope that by now you see that the difference would be represented by the difference in the coefficients for assistant and associate, where the expected difference is a 3.61. But if we look at our model, we don't have any information that would tell us if that difference is statistically significant or not. In some statistical packages, this is something we can test, but in particular, Gretzel does not offer this functionality, but we can redesign our model to be able to test it. Think for a second on what could we do to test the difference between an assistant and an associate professor. Note that since we excluded the instructor parameter, all our coefficients represent the difference between an instructor's salary and all the other ranks' salaries. So why don't we do the same, yet this time we exclude the assistant dummy variable, and instead we create a dummy variable that represents the instructor professor and use that in our model. This is the regression output of a model that excludes assistant and instead uses an instructor dummy variable. So in this case, if all three dummy variables are turned off, the intercept represents the salary of an assistant professor, which is going to be 106. Meanwhile, the coefficient for instructor is going to be a minus 41.71, and this is the difference how much less an instructor earns relative to an assistant. And let's very quickly compare this to our prior model, where our baseline was instructor, and note that the difference between an instructor and an assistant was a plus 41.71. So we're really representing the exact same phenomena, only that our baseline for comparison in the earlier model was an instructor. Now we're using an assistant as our baseline model. And the coefficient for associate is 3.61. And note in the regression output that even though this coefficient is small, it is statistically different from 0. The standard error of this coefficient is just a 0.64. And even if we subtract 2 times the standard error to our coefficient, we're not even close to 0. Our low p-value also signals that this coefficient is statistically significant. In conclusion, we have evidence that an associate professor does earn more than an assistant professor, and specifically about $3,600 per year. And let's finish this video by spicing things up a bit, and let's include all of our dummy variables. We're going to have a dummy variable to represent if a professor is a professional or an academic, which was the first dummy variable, professional, which we used to represent the qualification categorical variable. And we're going to have the assistant, associate, and full dummy variables to correspondingly represent the 4 ranks we just talked about. I'm going to let the interpretation of these coefficients to you, and try answering some of the following questions. Note that we have 2 qualifications and 4 potential ranks, so there are 8 possible combinations here. The first thing I want you to think about is what is the expected salary for each of these 8 potential combinations. Then I want you to think and test if the differences between the salaries of the different categories are statistically significant or not. That is my homework to you. Thank you very much.